Okay, so at the beginning of class today, I said that chemists really want to know how many atoms they're working with in the lab, because that will allow them to figure out how much new stuff or product they're actually going to produce. So we're going to talk about how we can count by weighing using something called Avogadro's hypothesis today. All right, so when atoms combine, they do so not based on their mass, but based on a specific ratio of atoms. So it's going to be important that we know exactly how many atoms we're working with. It's not good enough to just place the stuff on a scale and figure out what we're going to get out the backside. So here's an example of a chemical reaction that involves methane. Methane is the stuff on the far left side of the reaction, combining with oxygen to form its products, carbon dioxide and water. When these things react, when the methane and the water, methane and the oxygen react with one another, again, they do so not by their mass. It's not like 3 grams will always react with 4 grams of oxygen. Instead, they do so based on the specific ratio that they want to react with. So, in this case, one methane molecule will always completely react with 2 oxygen molecules. Again, this brings an issue, though, and we talked about this in class today. We can't just pick out a single methane molecule and 2 oxygen molecules. So we need to find a different way to indirectly measure the amount of molecules that we have. So we must be able to figure out how many atoms are in samples of reactants if we're going to find out how much stuff we're going to be able to make. We obviously don't want to use too much reactant because reactant costs money, so if you use too much, your product that you produce is going to cost too much money, and that's going to make your customer not very happy. So the question is, how do we count atoms? We can't do so individually. You'd be counting for a really long time because atoms are really, really small. So today in class we looked at the method of counting by weighing, and that was pretty effective for counting the popcorn kernels. We were able to look at the popcorn kernels. I was asking you, tell me how many are in there. We didn't have to count them each individually. If we knew the mass of a small sample of them, if we knew the mass of one of them, and we knew the mass of the entire bottle, we certainly could figure out the mass. We certainly could figure out the total number of popcorn kernels in the bottle. And this came out to like 8,900 or something. But the issue we have there is for the popcorn kernels, or like the piece of candy in the candy jar that Mrs. Hanson always does during volleyball season, we need to know the mass of one piece of each candy. And therein lies the total issue that we ran into early on when chemistry was first evolving. For atoms, that means the mass of a single atom, and we don't have the expertise to do that. So it's not possible at the time of Avogadro. It's still really hard to do. It's still really hard to do today. So this is where he had to start thinking, okay, I need to know the total numbers of atoms that I'm reacting together, but I can't count them. So what am I going to do? So he relies upon his original hypothesis. Remember his famous law. It says that equal volumes of gases had equal numbers of particles. Equal volumes of gases had equal numbers of particles. And again, there were some stipulations here. We needed to be at identical conditions. So I couldn't be outside with the balloon and Zach inside with the balloon because we'd be at different temperatures. Our balloons have to be at the same conditions. But what he finds is that there are different masses for each one of the gases when he's doing this. So the boxes that you see here, the orange, purple, and yellow boxes, are going to represent the balloons that we're holding. And let's say the one on the far left is hydrogen, and the one in the middle, let's call that oxygen, and the one on the far right, let's call that nitrogen. Now the hydrogen gas, if he fills his balloon up to the appropriate volume and he puts that on a scale, maybe let's say it has a mass of 4.32 grams. Let's say he does the same for the oxygen and he fills it up to the same volume. Now remember what his law says: equal volume of gases, equal number of particles. So he's now assuming that the hydrogen and the oxygen balloon are going to contain the same number of particles. He puts it on a scale and he finds out this time that the mass of the balloon is 69.12 grams. Well, that's considerably more than the hydrogen. Why would there be a difference in mass between the hydrogen and the oxygen if both balloons contain the exact same number? The only answer could be that the oxygen atom is bigger. Okay, he goes on and he does the same thing now for nitrogen. And that mass comes out to 60.48. Again, a different mass. Closer to oxygen, but still not the same. So Avogadro knows this. He knows that oxygen is quite a bit bigger than hydrogen. Nitrogen is about the same as oxygen, but different nonetheless. And as we did in the POGIL activity, we figured that we could do something with those masses to find out the relationship between one another. We found the relative masses of each one of the components. He did this with a bunch of gases. And over he kept on finding that hydrogen was the lightest of them all. So, he compared every one of the gases to hydrogen. He took the mass of his hydrogen sample and he just divided it by itself. And he gave the value of hydrogen 1 AMU, atomic mass unit. Like I said, he compared every gas to hydrogen. So he divides the oxygen by 4.32 as well. And if you do that on your calculator, you'll figure out that that's 16 AMU. And he does lastly the same thing for nitrogen. Divides by 4.32. And he gets a number very close to 14, and he calls that AMU. So this tells him that an oxygen atom, that his oxygen sample, is 16 times larger than his hydrogen sample. Remember, both of these balloons, actually all three, contain exactly the same number of particles. So what can be the reason for the different sizes? Well, it's got to be different sized atoms. And thus he says that the oxygen atom is 16 times larger than hydrogen, and the nitrogen atom is 14 times larger than hydrogen. Now I want you to pause the video, go to your periodic table, look for these three elements, and see if you can't find those numbers, 1, 16, and 14. Alright, so hopefully you've done that. We've got an issue. If you look at the periodic table, there's some gases on there, but the bulk of the elements on there are not. Most of the elements on the periodic table are actually metals. So we can ask the question, well, how do we find the masses for the non-gases? Well, here's what we knew. We knew that metals did a super job of combining with oxygen. Anytime you see something rust, you witness this. The iron in the particular metal is combining with oxygen to form iron oxide, which is rust. But it's not only iron that does this. Many, many, many other metals do this as well. So we figured, and Avogadro figured, that we could use the percent composition and the known relative mass of oxygen, because we found that in the previous slide, to find the relative mass of magnesium. And here's how we do that. Let's say, for starters, that we have a sample of 60 grams of magnesium. So here's our magnesium, and we have 60 grams. And we burn that magnesium. It's actually a really cool reaction. This is the reaction over here. It's a picture of it. It's really, really bright. We burn that magnesium. And we do so in oxygen. Okay. And the mass there, let's just go back for a second. Let's not think of it as being diatomic right now. That throws an extra loop into us. But if we combine 60 grams of magnesium with some oxygen, we get a new thing on the opposite side. These two combine in a 1-to-1 ratio. And we get 100 grams of this stuff. Okay, we get 100 grams of that stuff over there. So, how much of the stuff, the magnesium oxide, must be oxygen? Well, the answer is 40 grams, because 60 plus 40 gives 100, and the law of conservation of mass says that this side has got to be equal to that side. Okay. Now, what do we know about oxygen besides the mass that's being used in this particular example? Well, we know its relative mass. We found that on the previous slide. We called it 16. So oxygen has a relative mass of 16 AMUs. We don't know what the relative mass of magnesium is. So here's where our ratio is going to come in. I'm going to have to do a little bit of erasing here. Maybe not. Let's just do a different color. So our ratio of magnesium to oxygen in this particular reaction is 60 to 40. We know that in this particular compound that reacts with one atom of magnesium and one atom of oxygen, 60% of it will be magnesium and 40% will be oxygen. Well, we can relate that to the masses of each one of the materials. Oxygen has a relative mass of 16. So now we have to solve for the numerator, solve for x. And if you do that on your calculators, you're going to find that you get 24. And go ahead, get the periodic table. See if you can find 24. I bet you do. So we are going to do a lab in this particular unit that focuses on this idea and actually proves to us that, yeah, certainly this concept does work to be able to find out masses of each of the elements on the periodic table. All right, so let's continue. Oh, let me back up. Knowing the relative mass of elements is fine, since we never work with only a few atoms. So relative mass is okay. Again, I'm not exactly saying that the hydrogen atom has a mass of 1 gram. No, I'm not saying that at all. It's got a mass of 1 AMU. Well, what's an AMU? Well, who cares? We don't really care. We just need the relationship. We need the relationship that oxygen is 16 times larger than hydrogen. Okay, so magnesium is 24. But 24 what? I hate naked numbers in this room. So the 24 is the number that we refer to as the element's average atomic mass. We stick the word average out in front because this number is actually what I call a weighted average. As you've probably noticed from your periodic table, the atomic mass for magnesium isn't exactly 24, just as the average atomic mass for hydrogen isn't exactly 1. And this is due to something called isotopes, which I'll talk about a little bit later in this chapter. But 24 what? Well, when we're looking for an atomic mass, we use the units AMUs. So for magnesium, it's not just 24, it's 24 AMUs, or atomic mass units. So if you look at your periodic table and you go find carbon, you'll notice that there are 2 numbers alongside of carbon. One at the bottom on our periodic table is the atomic mass. The whole number is called the atomic number. The whole number refers to the number of protons that are in the element. The protons for an element are like the fingerprint or the social security number. Every element, carbon, hydrogen, oxygen, has a distinct and specific number of protons. If you change the protons, you change the number, and you change the element. And that's not always true for atomic mass. And again, we'll see that with hydrogen. So for right now, when we say magnesium has an average atomic mass of 24, it's 24 AMU. So one carbon atom, like I have in this picture to the right, has a mass of 12.011 AMU. But what does that AMU mean? Well, AMU is specific to one atom, or one molecule. And it's pretty rare that we actually deal with a single atom or a single molecule. But as we saw in the chicken and the quail egg pogo, mass ratio is always the same, whether you're working in kilograms, or pounds, or atomic mass units, whatever you want to work with. The mass ratio is always the same. For oxygen and hydrogen, it's 16 to 1. For nitrogen to hydrogen, it's 14 to 1. It's always the same. So 1 AMU of hydrogen and 16 AMUs of oxygen have the same exact number of atoms. How many? They both have 1. But AMU, well, it doesn't do us a ton of good in the lab. I don't have a scale that can read AMUs. But if the mass ratio is always the same, then 1 gram of hydrogen and 16 grams of hydrogen, of oxygen, should also have the same number of atoms. Now, how many atoms are in these samples? And in fact, that wasn't known for a really long time. Now, Avogadro didn't come up with his own number. Someone else did. Someone else after he passed away. But in actuality, to figure out the amount of product that you're going to produce, we don't need Avogadro's number. You'll see that later on down the road. But eventually it was figured out by looking at the sizes of individual atoms and the volume that they take up. And it was concluded that Avogadro's number, or 1 mole as we call it, is 6.022 times 10 to the 23rd atoms. So if you've got 1 gram of hydrogen, you have 6.022 times 10 to the 23rd hydrogen atoms. If you have 16 grams of oxygen, you have 6.022 times 10 to the 23rd oxygen atoms. This is known as Avogadro's number. Every single one of those average atomic mass units that you see on the periodic table, you can think about the units of those numbers in AMUs and also in grams. But if you think about them in AMUs, then you're talking about single atoms. If you're talking about grams, you're talking about a whole mole of atoms. And I like this picture in the lower right-hand corner. I think it's quite interesting. There's 6 different samples. Mercury oxide, sucrose, which is just table sugar, sulfur, copper 2-sulfate pentahydrate, just regular copper, and sodium chloride, or table salt. And what's interesting is that each one of these samples has exactly the same number of molecules inside of them, or atoms. So the copper that you see on the far right side has 6.022 times 10 to the 23rd copper atoms. The sucrose, or the table sugar, the white stuff on the left, has 6.022 times 10 to the 23rd sucrose molecules. And the sulfur has 6.022 times 10 to the 23rd sulfur molecules. There you go. So that's the mole. And this is kind of a funny little cartoon right here. There you go. All right.